Hi. Thank you guys for having me. As was mentioned, I'm going to be talking about how to build private applications easily using the Sunscreen FHE compiler, stands for fully homomorphic encryption, and Rust. And the T sommelier component was while I worked at Meta, so you have to choose your title. And I also did want to mention that after this, there's a talk that was kind of added last minute. It's called Effectful by Powell, and Effectful is a effects library in Haskell that has blazing speed and amazing ergonomics. So please come and watch that one as well. So when we're processing data and when we're giving data to third-party servers, we need to trust those third parties to keep our data safe. So oftentimes when we're just communicating with the server, ideally if a server is set up well, the first thing that we do as a line of protection is that we encrypt the data as it goes towards the server, right? So the user will have some sort of data that they have. They will then encrypt it, often sending it over a channel like HTTPS, and send it to the server. Now, once the server has it, they'll have it in a decrypted form so they can actually do some data processing on it. The server will then produce whatever result you want, and then afterwards will likely also encrypt the information and send you some result back. There's an interesting part about this when we think about data privacy and whether or not users really have control over this data, is that this data, since it's processed in the clear, it needs to be processed in the clear, right? So essentially an online shop needs to know what you bought, and it also needs to be able to contact your credit card company and actually perform an exchange and stuff like that. And maybe, and this will come up a little bit later, maybe some health-related services like a DNA service will need to know some health data about you in order to, say, find relatives related to you. Right, so fundamentally, if we just gave them the encrypted data, they couldn't do anything with it if it was encrypted on the server side. So the question is, can we really trust third parties with our data? So I would say that there's a few different cases that come up where we might not have full trust. One is data misuse. So here we can have data profiling in the case of maybe what was kind of famous at the time was Cambridge Analytica. So Cambridge Analytica was maybe data that shouldn't have been shared with a third party, right? So we could argue as to whether or not they should have had access or not, but potentially the users didn't necessarily expect for their data to be shared that way. Maybe another case actually that happened personally for me is I got a letter in the mail once that was your data has been breached through this medical professional, this third-party medical service that I had never heard of. So essentially my data that had been shared with the hospital had been shared with a provider, that had been shared with a provider, that had been shared with a provider, and someone way down the chain did something I didn't want with it. Another case of where you potentially can't trust a third party, and this is somewhat not necessarily the third party, but how the data gets through the third party, is malicious actors. So there was a man-in-the-middle attack for actually the Equifax website. So at one point while people were trying to use the Equifax website, there was someone who set up some fake domain that looked very similar to it, and people would log in, and then essentially people would be able to steal your financial data or information about your credit reports, freeze your credit or unlock your credit, that type of thing. And then even in cases where there's you could trust the person that you give the data to, there can still be data breaches. So an example of this one is the 23andMe data breach. So essentially 23andMe had a bunch of data, genetic data, related to who is related to who. And a lot of that data was exposed during a data breach. Now, ideally, in good faith, I would trust most of these services to kind of operate on my behalf and as part of the contract that maybe you sign with the terms of service. So even though they're potentially trying their hardest to prevent a data breach, these things can still happen. It's not necessarily the fault of the company, it's just that there are people, data is valuable and people want it, right? So the takeaway is that even if we trust a third party to do the right thing, our data is still not necessarily safe. So the question is, can users keep their data privacy while still using their favorite apps, while still using Equifax, while still using 23andMe, or being able to purchase online? And my answer is yes, emphatically yes, using something called fully homomorphic encryption, which is the technology that I work on. So what is fully homomorphic encryption? So homomorphic encryption allows data to be processed while remaining encrypted. This means that it's never decrypted at any point during the computation. So for example, we would have it defined maybe by this equation. Say we want to add two integers, a and b. There's two ways you can perform this operation. The first one is to take a and b on the right side of that equation, add them together normally, and encrypt the result. But it turns out that there's an equivalent operation you can do on encrypted data, which is the one on the left. Essentially, you encrypt the value a, you encrypt the value b, the definition of addition looks a little bit different, but you essentially do the add, and the result is a piece of encrypted data that contains the message A plus B. So maybe if we were to look at it in terms of this diagram, you can either kind of choose the top path, or you go A plus B and calculate that result and encrypt it, or you can go on the bottom path, encrypt the two inputs, and then just add them together. So the fully part of fully homomorphic encryption means that any computation can be performed on encrypted data. So there is a caveat here. When you're performing on encrypted data, it is larger, and it does take more time to process that encrypted data. So you're not necessarily getting like the same speed you would get on what's called plain text data, the unencrypted data, and also not the same size. So let's rethink the model that we have for a traditional application. For a traditional application, you would send your data to the server. It would then process your data in an unencrypted form and send you the result back. Here, in an FHE application, the user has control as to whether or not where their data is private. Essentially, the user has a key, represented by that icon there, and encrypts their own data, and then sends it to the server. Now notice that the server doesn't actually have a key here. They can't do anything to try to decrypt that data, but they can process it for you. They can produce that result and send it back to you, and then the user will likely want to decrypt their own data and see what the result was. So why isn't FHE used more currently? Well, they're a little bit difficult to use. Users need to know a lot about cryptography to choose the right parameters for a system. Also, making a computation performant is difficult, even for experts. So the way that you set up how you do a computation, even things like maybe you want to take x to the fourth power, like doing just x times x times x times x will be different than x times x, storing that, and then multiplying it by itself. Those two things can give you drastically different performance times. You can get incorrect results if you perform the processing incorrectly. So basically the way FHE works is it's often based on this thing called the learning with errors problem, which involves adding noise into the encrypted data. If you process the data too much, then the noise will grow so much that you can't decrypt the data properly. So you need to know exactly, you can't measure the noise, but you need to know how much you can do before you violate what's called the noise budget. Then it's hard to translate problems into FHE primitives. So FHE primitives are often addition to multiplication. That's how homomorphic encryption systems are either additively homomorphic or multiplicatively homomorphic. Full ones have both properties, but how you define like credit card fraud in terms of addition and multiplication, that's a hard concept, right? So that's why it's kind of difficult to currently use FHE. And that's where the Sunscreen FHE compiler comes in. So Sunscreen is the company that I work at, and we have a compiler in Rust that will take your programs that are written in Rust and convert them into FHE programs. So let's look at an example here. Here's the add function in Rust. It's very simple for integers. You just define that you've taken two types that are signed, and then you return a signed result, and then you just do the normal addition. Now the translation for this into the FHE component is really quite simple. There's just a few different pieces. First, you add this little decorator on top that says that you're going to be writing an FHE program and the specific scheme of FHE that you want to use. Currently, we mostly support BFE, but we're working on this other scheme called Torus FHE. And then additionally, the types change slightly. So here, you can see that the type says cipher of signs. So instead of just having an I64, we have our own types that are kind of related to things that you can do in an FHE program. Now, how would you actually run this thing? So to run this thing, essentially what you do is you have an application, which is you instantiate a version of the compiler with compiler.new, and then you tell it the FHE program you want to compile. So encrypted add was the name of the function that we had before, and then .compile is to actually do it. And additionally, we have this other kind of object called a runtime. So the runtime keeps track of a whole bunch of things for us related to the keys related to producing that you can use to encrypt data and decrypt data. And it needs to know the specific application. So if your application is more complex, you'll probably have more complex parameters related to your program. So you need to basically have runtime depend on the application. And then you can pull out the encrypted program from the compiler. Then what you can do is you can generate keys, and then this is very similar to just any asymmetric key encryption system. And then you can encrypt data. Here we're taking 15 and 5 and encrypting it under our public key. And then we run the program that we had before, that add program, with inputs. Now here you can see the inputs are specified as a vector, and they're converted into an FHE input type. So essentially what this will do is it'll run our add program with that encrypted 5 and 15. And then the public key is required because potentially what could happen is that if you add in certain types of data, the program might need to encrypt stuff on your behalf. So the public key allows anyone to encrypt data for you, and the private key allows you to decrypt that data. But only the private key holder can decrypt it. And then what happens is that we can have the runtime, after we get the result from the program, we can call the decrypt function with our private key. So what kind of operations does Sunscreen support? So Sunscreen supports some kind of basic types that you might expect. We have integers, and with integers you can do addition, subtraction, and multiplication. And you can also do it between different types. So you can, different plain text and encrypted inputs. So you can have basically one of your inputs be an encrypted number, one of your inputs be an unencrypted number, and then run it still. We also have a signed type, and then it has all of the properties that you would have for the unsigned type, except for you can also negate the value. We have a fractional type, which you can kind of think of as like fixed point, or more generally maybe floating point. It's not exactly floating point, fixed point is much closer. So that has all the properties of signed. The end part related in there is the number of bits of precision after the decimal point that you have. And then you can divide by an F64 constant. So then that will basically say like that is a plain text number, so that you can divide by say 5, but you can't divide by an encrypted 5 here. And then we have another type here called rational. So rational has the same base properties as signed, but you can divide by an encrypted value. So the reason also these are in this type of order is because as you go down this list, it takes more space and more time to compute on these operations, on these data types. So essentially, actually what a rational is it's two signed values, the numerator and the denominator. And that's how you end up being able to do division. So encrypted values are wrapped in this cipher type. So as you've probably seen in some of the other examples, cipher of T denotes that you have like some underlying value T that is encrypted. Now note that there is no way to create this wrapper yourself or just like use new on it. You have to use the runtime to encrypt a value to generate a value of types that has the wrapper cipher on it. And then one thing that's kind of nice about our library is that you can also kind of test it in both the plain text variant and in the encrypted variant. So this is nice because like if you just had encrypted values, you might not be able to probe exactly what's going on in the circuit or in the program and be able to figure out precisely like where something went wrong. So how you do this is that essentially you are generic over either addition or multiplication or both for the operations that you need to do. So here you can say that our add generic is generic over some type T, where the type T has an add that can take two T's and produce a type T, and also has the additional constraint of copy. And then if you want to actually use this in an FHE program, you add all the decorators that we had talked about before and just add in specific types. So one thing that's important to notice here is that you will have to like write that bottom part, the encrypted add from generic. You'll have to write a unique one for each type that you want. So if you wanted to operate on unsigned versus signed, you will have to write 2 of those. But you could also generate a macro that would generate all the definitions for you. You can mix encrypted and unencrypted values. So here, as we mentioned, that you can say add, but where A is a cipher and B is a plain text value. But in this case, notice that the output is always encrypted. So you will never do this and produce an unencrypted value. That would break the cryptography and you have a very insecure system. And we also support, we don't support vectors, but we support arrays. So essentially, you can have arrays of, in this case, some type T, where we're then doing addition. And here, you would be able to add a array of size n together in order to get the sum. So here you can see, specifically, you also have to include that size n, because essentially the compiler needs to know how many additions it's doing in order to generate the correct parameters. But then you can call this function here. One important caveat here is that you cannot use vec. So you cannot use anything that's dynamically sized, because we can't figure out how many operations you're going to do. There are some restrictions when you try to do this type of operations. So essentially, comparisons are not supported. So you cannot do something where, say in this case, where you take in a select number, and you want to say, like, if the select is 1, then I will return the first ciphertext, otherwise the second one. You can't do that under the BFB scheme. Similarly, or one thing that is important to note here is that you can do comparisons if it's on plain text values. So here in this example, we have a for loop that goes from 1 to 5, and then inside there's a conditional there that says that if that I is modulo 2 is equal to 0, that part's fine. Because we're not actually doing any comparisons on encrypted data at that point. We also can't do variable loops because, as I mentioned, the compiler needs to know exactly kind of what computation you're running. So here, this would be an invalid program because it takes an assigned value for the size of the for loop. But if we change it to be something where we actually know the size, here we go from 0 to 5, we can do this. So we can say, like, if I know the certain number of loop operations I need to do, then I can compile this program. There are also some operations that are a little bit leaky, so our compiler will complain at you if you try to do them, and they make a lot of sense. So like, basically the two main ones are you can't subtract a ciphertext value from itself. The reason why is because if you subtract all the bits, you would get 0, and everyone knows you have 0 now. there's an unambiguous value there. And similarly, if you multiply by 0, again, all the bits are 0, so you know that value is 0. It is a valid encryption. 0 is a valid encryption under every key that you could ever generate, but it's also very obvious what you've encrypted at that point. There's also a bound on the amount of operations you can perform. So here, I've done a loop of size 100. So essentially, I mentioned there was about a noise that was added into your ciphertext, and that grows to a certain extent. There is a limit to how many computations you can do. Our compiler will complain at you if you try to do too many. I did want to mention that as of recently, we've added something, we built our own cryptography library on this thing called Torus fully homomorphic encryption that does allow you to do comparisons. And so we are working on kind of building out that and adding some things on top of that. But then that would allow you to essentially do that encrypted. If I have my bit is 1, then if my bit is 0, I'll select A, otherwise I'll select B. So with that, let's get into some examples of FHE programs. So we're going to go through 3 different examples in this case. One is we're going to go through a private ML inference example, which is doing credit card fraud detection. Another one that we're going to talk about is private auctions. And the third one is called dark pools, which are a financial instrument in both traditional finance and in crypto markets. So for the private machine learning case, you can do FHE-based model inferences. You can do model training as well, but model inference is a little bit easier. What this allows users to do is to keep their data private when running it through your model. And additionally, the other property here is that the person who owns the model, if you're sending it up to their server, their model stays with them, so it's also private to them. So we're going to go through credit card fraud detection. Another example might be if you wanted to do, say, private ChatGPT. You could do private ChatGPT where you submit your query to the server, it would produce the response for you. OpenAI would never know what you asked it, and you would never get the weight models from OpenAI to actually run it yourself. So everyone gets what they want. So for that one, there we go. Let's look at the credit card example. So here, exactly what's happening here is that we're going to look if a transaction is fraudulent. I'm actually going to start this by just doing the prediction. So what the user would do in this case is that they're trying to figure out whether or not a transaction has any problems. So here, say the transaction happened 5 miles from home with a purchase price of $500. Maybe they're half a mile away from where they previously made a purchase. And the median price of this thing is $480. And there's some other Boolean values here as to whether or not like a chip was used, a pin was used, if it was used in person or not. So you could basically do predict securely. What will happen is the data is encrypted under the user key. It's sent up to the server to be run through an ML model. The ML model will be able to process that data for you and figure out whether or not the transaction is legitimate or not, but the server won't actually know if it's legitimate. Only the user will know. So the server can send back that data to the user to be decrypted, and they can figure that out, but the server will never hold that data. They will never know whether or not that transaction was valid or was fraudulent or not. Now here in a case where we have something that's a little bit more like fraudulent looking, essentially it's 500 miles from home where the purchase price is $500 when you normally expect $50 for that item, so 10 times more. And you're way far away from the last time that you used something, and it was only online. So here we can see that we're sending up this data, and we actually found fraud instead. So That's the first example. And the second example is something called blind auctions. So in blind auctions, what you do is that basically instead of having an auction house where everyone's like raising their little bid things and you know what everyone else is bidding, what happens is that everyone places in their bids all at once, and then you choose the maximum. So normally someone knows exactly what this value is, but in the FHE, or what all the bids are, but in the FHE case, essentially not even the operator of the auction knows what the bids are. So all bids are private. The winner can be determined from all of the encrypted data. You can basically select the maximum of all of the bids, and then the winner would reveal their bid. And the benefits of this is that you don't reveal your bid if you lose. So there's a case of this actually, another case of this called the Dutch auction, which is used for tulips in the Netherlands. And essentially what happens is that they have this clock that just goes down, and then you raise your hand when you want to select it. And what's good about that is that no one else's strategy for how they want to buy those flowers is revealed. So in this case, we wouldn't reveal any of that. And also, often this type of bidding leads to more genuine bidding for the value of the object. Instead of saying, like, I want to beat out this other person, or I see their trading strategy, no one knows anyone else's strategy here. So can we do this without trusting a third party to compute the winner? The answer is yes, as one could imagine. So here is an example of what a blind auction would look like. Here there are 92 bids total, 92 because that's what fits nicely in a square here with you pull out the center. And essentially what you want to do is you want to put in a value. In this case, it's based on Ethereum, so it's the amount of GUI that you're spending. And you want to participate in the auction. So here, what happens is that it will encrypt all of those values. All the values are encrypted by those different users. And then you compare all of the values and see who has the maximum. And here you can see that I didn't win. Bid number 72 won. So normally no one would know what this is. In this application, in this demo, we have it, you can click on here and you can see that someone bid 7.9 or 6.9 million. But you can see also here if I specify 7 million, ideally I should win the auction. If I don't, that will be interesting. Yeah, you are the winning bid. So I would then reveal that to whoever the network operator is. And then the final example that I have is what are called dark pools, and I'm calling them truly dark pools. So dark pools are a financial instrument that allow investors to place large orders without altering the market, alerting the market to their intentions. So examples often include like large institutions like banks who want to trade assets that might be difficult to fulfill with other banks. If they do this through what's called the lit market, then essentially their intention would be revealed and people would then put in options to either like what's called front running, where they might try to like change the value of the price underneath that bank to either be more favorable for them or to be malicious to the bank. Additionally, what dark pools allow you to do is to hide your trading strategy. So this is sometimes called protecting your alpha. And what we can do with FHE is we can make it so that you essentially build a dark pool where the order book is private, and even the person who runs the dark pool, who would normally in traditional finance be able to see all the bids and could potentially front run you and like do malicious things to you, even that person doesn't know what the bids are. So in this case, what we're going to do is this is a final example we have. And I should mention all these examples are not running on my computer. They're essentially, I'm encrypting the data, sending it up to AWS, and then getting the result back. So here, I'm going to put in a value of I want to trade 1 ETH for 0.049 Bitcoin. So I can submit that encrypted order. Oh, well, okay. That I thought might happen. There we go. Yeah, so here you can see it's unfortunately really tiny on the screen, but it says it's submitted successfully. So here what happens is I have a bid in the dark pool. And so essentially the dark pool knows that I have an order in there, but it doesn't know for how much exactly I want to trade and what the limit price is. We have it in here that you can basically like figure out like what the amount was based on the decryption, just for an example, but otherwise no one would know exactly what this was. And then say another person comes along and wants to perform the opposite trade. They wanted to sell instead of buy. Well, if they submit their order, they submit it successfully, and then you'll see actually my order is gone now because my order has been fulfilled. And so it's now outside of the market, or outside of the dark pool, and I can now extract the funds or get the Bitcoin that I wanted or the Ethereum that I wanted. So with that, that's a kind of whirlwind tour of the FHE compiler that makes it easy to make privacy-preserving applications. So the values of this is it reduces malicious data use, it reduces the effects of data leaks. So even if a trusted third-party provider does have a data leak, you don't have to worry as a user that your data is actually going to be compromised. And it gives users control of their data security instead of having the actual third-party processors having control of their data security. And with that, that's the end of my talk, and thank you for coming.